So in section 2.2, we're going to continue working with limits, but we're going to work with limits involving infinity. Now there are two ways that these limits get done. One is we can have limits where x is going to positive infinity or x is going to negative infinity. Now remember, infinity is not a number, it's the idea of an ever larger number. So when I say x is going to infinity, we keep going way out to the right graphically, but we're going so far to the right that we can't even imagine how far right we are. Or if x is going to negative infinity, we're going left on the graph, but we're going so far left we can't even imagine how far left we are. We're going to do these after we talk about the y going to positive or negative infinity, because these are the tougher ones to do, because we can't really use graphs to help us. So calculators are not a help. Sketching the graph is not a huge help, because these happen at such extremes to the left and right that we can't even imagine how far away they are. In this video, we're going to focus on what if y goes to positive or negative infinity. This is a little bit easier for us because you've actually kind of done this, because these are for vertical asymptotes. So I needed to do a quick review of vertical asymptotes, and then we'll talk about the calculus of them. So vertical asymptotes generally occur at x values which make the denominator 0 and do not cancel out. I say generally because logarithms have a vertical asymptote, but I need to get you comfortable with just remembering and working with the vertical asymptotes of rational functions before we worry about the logarithm ones. So again, in a rational function, if they make my denominator 0, in other words, the function doesn't exist there, and I can't cancel away that discontinuity. So in the example I have down here, the example I have down here, I can see from this function that what would make my denominator 0 would be x plus 2 equals 0 and x minus 3 equals 0. So I have x equals negative 2 and x equals 3, where my function doesn't exist. But I can also see that I can simplify my function by canceling out the x plus 2's, leaving me with 1 over x minus 3. In this case, what caused x equals negative 2 to be a discontinuity got canceled out, so x equals negative 2 as a whole. What caused x equals 3 to be a discontinuity did not cancel out, so this is a vertical asymptote. So I know graphically there is a vertical asymptote here at 3. I'm not going to put the whole yet because we need to talk about how do I know what the sketch of this will look like, but when I do graph it, it's going to look like 1 over x minus 3, but there'll be a hole at x equals negative 2. So then, oh, I'm sorry, let me go back. One thing to note here, functions are not allowed to cross a vertical asymptote. Mathematically, the word asymptote is a line that a function approaches. Vertical asymptotes can never be crossed, not because it's an asymptote, but because we're dealing with functions. If I cross a vertical asymptote and then try to come back closer to it because it's an asymptote, I violate the vertical line test and it wouldn't be a function. So in this graph, if I had a function that's coming up here and it's getting closer and closer and closer, but then it crosses the vertical asymptote, because it's an asymptote, it would have to come back. And I could have something like this, but now the red is no longer a function. So it's not because it's an asymptote that we're not allowed to cross it. It's because it's vertical and would result in not having a function that we don't cross it. So the calculus for vertical asymptotes is just looking at to see what happens to y as we approach a vertical asymptote from either side. And for these, you really can't do substitution because the function doesn't exist, and if you simplify it, you still end up with 0 in the denominator. That's how we actually found it's a vertical asymptote. So it's a little annoying we can never use substitution or even simplify and substitute for when we're dealing with vertical asymptotes. But what makes things easier for us is that there are only two possible answers for a limit as we approach a vertical asymptote. Either my function is going to positive infinity or my function is going to negative infinity. That is it. We do look at each one-sided limit because they might be going to different infinities. On one side, y may be going up to positive infinity. On the other, y may be going down to negative infinity. So the easiest methods are, if you're allowed to use a calculator, just graph on your calculator and take a look. If you are not allowed to use the calculator because on the AP exam, about 2/3 of the exam is no calculator, make a simple table where you're just plugging in like 2, maybe 3 values as you approach from one side, and just see, are my y values as I get closer to the asymptote getting bigger or smaller? If they're getting bigger, the limit's going to be positive infinity. If they're getting smaller, the limit's negative infinity. So to go back to our example here, we already said that there is a hole at x equals -2 and a vertical asymptote at x equals 3. So I can put my vertical asymptote in because this simplifies to 1 over x minus 3. If I then do my limit, and I'm going to approach from the right side first. So x is approaching 3 from the right for my function. I can't plug in 3 because I'll end up with 1 over 0. I can't simplify 1 over x minus 3 anymore. So I'm going to use a table. And a lot of times we just kind of do this in our heads or kind of off to the sides. It's rare that we write a full table. Well, I'm just going to pick two numbers that get closer to 3 from the right. So I'm going to use 5 and 4. I can use the simplified version of the function to make this easier math. So if I plug in 5, that's 1/2. If I plug in 4, that's 1. And I can see that as I get closer to the vertical asymptote, my y's are going up like this. So this limit is in positive infinity. If I then approach from the left-hand side, I'm going to take the same approach, just from the left. And again, I'm just going to pick a couple of numbers coming closer from the left. So I'm going to use 1 and 2. And using the simplified version of the function to make the math easier, if I plug in 1, that's -1/2. If I plug in 2, that's -1. And I can see now that as I get closer from the left-hand side, my y's are going down. So this limit is going to be negative infinity. And if I extend this out, there'll be a hole here at x equals 2, as we said. And now we have a sketch of this function.